The universe is an endless ocean of mysteries, a place where the ordinary rules of reality seem to bend and twist into the extraordinary. Out there, beyond the shimmering veil of stars, lie objects so bizarre, so utterly baffling, they defy everything we think we know. Picture a star that shouldn't exist, a planet with skies of molten glass, or a black hole spinning so fast it warps the fabric of space itself. These aren't fragments of science fiction, they're real discoveries, waiting to unravel the secrets of the cosmos. And today, we're diving deep into 25 of the strangest objects ever found in space, each one more puzzling than the last. Think about the last time you looked up at the night sky and felt that tug of wonder. Maybe you spotted a familiar constellation or caught the glint of a distant planet. But what if I told you that hidden among those twinkling lights are things far stranger than anything we've dreamed up? Objects so peculiar they've left even the sharpest astrophysicists scratching their heads. From rogue planets hurtling through the void without a sun to galaxies that spin backward against the cosmic grain, the universe is a treasure chest of oddities just begging to be explored. And the deeper we look, the more we realize space isn't just vast, it's downright weird. This journey isn't just about listing curiosities, it's about stepping into the unknown where every discovery rewrites the rules. Imagine stumbling upon a star made of diamond or a cloud of alcohol floating light years away. These aren't just fun facts, they're clues to the grand puzzle of existence, pieces of a story billions of years in the making. So buckle up, because we're about to venture into the cosmic frontier where the impossible becomes real and the strange becomes unforgettable. By the time we're done, you'll never look at the night sky the same way again. The Black Widow Pulsar is the cosmic equivalent of a predator lurking in the dark, a neutron star with a taste for destruction. Discovered in the late 1980s, this celestial menace spins at a dizzying rate, blasting its companion star with deadly beams of radiation so intense they're literally stripping it apart, atom by atom. The pulsar earned its name for a chilling reason. Just like the spider that devours its mate, this star is slowly consuming its partner, leaving behind a trail of stellar debris. What makes this object even more extraordinary is its speed. Rotating hundreds of times every second, the Black Widow Pulsar generates magnetic fields trillions of times stronger than Earth's, whipping particles into a frenzy and launching them into space at nearly the speed of light. This isn't just a cosmic oddity, it's a natural particle accelerator, a place where the laws of physics reach their limits. Astronomers first detected its presence through rhythmic pulses of gamma rays, the signature of a pulsar, but something was off. The signals weren't steady, they flickered as if something was interfering. That's when they realized the companion star, a small, dense object, was being systematically torn apart by the pulsar's relentless energy. Today, all that remains is a ghostly wisp of gas, the last remnants of a star that once shone brightly before meeting its grim fate. This isn't just a tale of stellar destruction, it's a glimpse into one of the most violent and extreme processes in the universe. The Black Widow Pulsar challenges our understanding of how stars evolve, how energy behaves at the edge of possibility, and what happens when cosmic neighbors turn deadly. And as astronomers keep watching, they're uncovering even more secrets, hints that this might not be the only predator lurking in the depths of space. The Red Rectangle Nebula is like a cosmic stained glass window suspended in the void, a masterpiece of geometric precision where nature defies its own chaotic tendencies. Located about 2,300 light-years away in the constellation Monoceros, this striking structure earned its name not just for its vivid hues but for its near-perfect rectangular shape, a form so unnatural for space that it left astronomers baffled for decades. Most nebulae billow in wispy curls or explosive spheres, the aftermath of dying stars, but this one, it's all sharp angles and symmetry as if drawn by an invisible architect. At the heart of this enigma lies a binary star system, two aging suns locked in a gravitational dance, their interactions sculpting the nebula's bizarre form. The primary star, a post-red giant, pumps out vast clouds of gas and dust, while its smaller companion funnels that material into twin cones, creating the illusion of a glowing X when viewed from Earth. The sides of the rectangle, those are the edges of the cones, illuminated by starlight bouncing off dust grains finer than powdered snow. But the real showstopper is the color, a deep, almost eerie red that bleeds into shimmering blues and greens along the structure's edges. This isn't just cosmic artistry, it's chemistry in action. The red glow comes from a rare form of carbon molecules called polycyclic aromatic hydrocarbons, lit up by the star's ultraviolet radiation. Think of it like interstellar neon, a signpost written in elements that shouldn't survive long in space, yet here they blaze defiantly. Theories about how this structure formed read like a detective novel. Some suggest the star's orbit acts like a spinning garden sprinkler, flinging material outward in precise jets. Others propose that a thick disk of dust around the binary system acts as a stencil, shaping the escaping gas into those razor-sharp lines. But the truth, we're still piecing it together. Every new observation, from Hubble's crisp images to infrared data revealing hidden dust layers, adds another clue to the puzzle. What makes the red rectangle truly extraordinary isn't just its appearance, it's a time capsule. The binary stars are nearing the end of their lives, and in a few thousand years, their intense radiation will shred the nebula entirely. We're witnessing a fleeting moment in cosmic history, a structure so rare that nothing quite like it has been found elsewhere in the galaxy. It's a reminder that even in the vast, cold expanse of space, beauty thrives in the most unexpected forms, and sometimes it comes with edges. Hoag's object is the universe's way of showing off its flair for the unexpected, a galaxy so bizarrely perfect. It looks like someone dropped a cosmic hula hoop into the void. Discovered in 1950 by astronomer Arthur Hoag, this enigmatic structure floats 600 million light-years away, a pristine circle of blue stars surrounding a golden core with nothing in between. No spiral arms, no messy dust lanes, just a luminous ring floating serenely around an empty center, as if the galaxy forgot how to fill in the middle. What makes this so strange? Every other galaxy we know of, spirals, ellipticals, even irregular ones, follows predictable patterns of formation, their shapes sculpted by gravity and collisions over billions of years. But Hoag's object defies all of that. Its symmetry is unnerving, a bullseye so precise it feels intentional. The ring, packed with young, blue stars and glowing hydrogen gas, spans roughly 120,000 light-years, while the core at its heart holds older, redder stars. And separating them, a yawning gap of near-total darkness, a cosmic moat with no obvious bridge. Theories about how this could exist range from the dramatic to the downright speculative. One leading idea suggests a bullseye collision billions of years ago, where a smaller galaxy punched straight through a larger one, triggering shockwaves that compressed gas into a star-forming ring. Picture dropping a pebble into a pond, except instead of ripples, you get a perfect circle of stellar fireworks. Another hypothesis points to gravitational instabilities, where the galaxy's own rotation spun its outer layers into this bizarre hoop while the center collapsed inward. But here's the real kicker. Hoag's object isn't entirely alone. Peering into the darkness around it, astronomers spotted another, fainter ring galaxy lurking in the background, almost as if the universe decided to double down on the mystery. Could this be a clue or just a cosmic coincidence? Nobody knows for sure. What's undeniable is how this celestial oddity forces us to rethink the rules. Galaxies aren't supposed to look like this, yet here it is, glowing defiantly against the blackness of space. It's a reminder that out there, beyond the edges of our textbooks, the cosmos still holds puzzles we haven't even begun to unravel. And every time we point a telescope at Hoag's object, it whispers the same tantalizing question. What else are we getting wrong? Fast radio bursts are like the universe's cryptic text messages, blaring into existence for just milliseconds, then vanishing without a trace. These intense bursts of radio waves pack more energy than the sun emits in days, sometimes even months, yet they last shorter than the blink of an eye. First discovered in 2007, these signals have sparked everything from rigorous scientific debate to wild speculation about alien civilizations trying to get our attention. But the truth, it's even stranger than fiction. The mystery begins with their unpredictability. Some FRBs repeat at irregular intervals, while others fire once and never return, making them nearly impossible to catch in the act. Imagine trying to study a lightning bolt that strikes randomly across the cosmos. No pattern, no warning, just a split-second flash of energy from billions of light-years away. That's the challenge astronomers face. Possible explanations range from the mundane to the extraordinary. One leading theory points to magnetars, highly magnetic neutron stars that occasionally unleash starquakes, violent ruptures on their surfaces, releasing enough energy to be detected across the universe. Another suggests cosmic collisions, like two neutron stars spiraling into each other, creating a gravitational fireworks show that reverberates as a radio burst. Then there's the more speculative angle. Could these be signs of advanced technology? Some have proposed that FRBs might be leakage from alien light sails, ships harnessing unimaginable power to traverse galaxies. While there's no concrete evidence, the idea isn't entirely dismissed after all. Before pulsars were discovered, their precise signals were briefly mistaken for possible extraterrestrial beacons. What makes FRBs particularly tantalizing is their ability to map the universe's hidden matter. As these bursts travel across space, they interact with electrons, slowing slightly in ways that reveal the density of cosmic material between galaxies. They're not just mysteries, they're tools helping us probe the invisible scaffolding of the cosmos. For now, every new detection adds layers to the puzzle. Some FRBs arrive with a twist polarized signals that suggest they've traveled through extreme magnetic fields, possibly near black holes. Others come with a lower frequency afterglow, hinting at environments more chaotic than we anticipated. With each clue, we're not just chasing answers about these bursts, we're unraveling the universe's most extreme conditions, 1 millisecond blast at a time. Imagine a world where the ground beneath your feet isn't rock or ice but solid diamond, glittering under the light of a dead star. That's PSR J1719-1438b, a planet so ludicrously exotic it seems ripped from the pages of a sci-fi novel. Discovered in 2011, this cosmic jewel orbits a pulsar 2,500 light-years away, and its very existence shatters what we thought possible about planetary formation. Most planets are born from the dusty leftovers of star formation, a mix of silicates, metals, and gases. But this one, it's the remnants of a star itself, a celestial phoenix transformed into something utterly alien. The pulsar it dances around a rapidly spinning neutron star was once part of a binary system. Over eons, its gravity siphoned material away from its companion, stripping it down to a corpse so dense, the remaining carbon crystallized under unimaginable pressure. The result, a planet roughly 5 times Earth's mass compressed into a sphere of diamond. The conditions that forged this world are beyond extreme. Picture pressures so intense they crush carbon atoms into a crystalline lattice, temperatures soaring high enough to melt steel, and a gravitational tug so fierce it distorts the fabric of space-time around it. Yet against all odds, this diamond didn't just survive. It thrived, orbiting its pulsar in a breakneck 2-hour loop. Astronomers caught hints of its existence through tiny wobbles in the pulsar's radio pulses, a telltale sign of an unseen companion's gravity tugging at it. But when they calculated the planet's density, the numbers defied logic. Too lightweight to be another neutron star, too dense to be a gas giant. The only explanation was a carbon-rich composition, a diamond in the cosmic rough. What makes this discovery revolutionary isn't just the spectacle of a gemstone planet. It's proof that planets can form from the ashes of stellar cannibalism, in environments so hostile we once thought them barren. If diamonds can bloom in the graveyard of stars, what other impossible worlds are waiting out there? The universe, it seems, has a flair for the extravagant, and this glittering oddity is its most dazzling encore yet. Somewhere beyond the Milky Way's shimmering veil, a cosmic titan lurks in the shadows, an invisible force so powerful it's dragging hundreds of galaxies toward it at breakneck speeds. This is the Great Attractor, a gravitational nightmare hiding in plain sight, warping the fabric of space itself. For decades, its existence was little more than a frustrating rumor, its secrets buried behind thick clouds of interstellar dust where telescopes couldn't pierce. But what we've slowly uncovered is a mystery that redefines our place in the universe. The story begins in the 1970s when astronomers noticed something bizarre. Galaxies in our corner of the cosmos, including the Milky Way, were all streaming toward the same patch of sky near the constellations Centaurus and Hydra. It wasn't just a gentle drift, they were racing at over 14 million miles per hour, as if pulled by some unseen hand. The problem, when they looked in that direction, there was nothing massive enough to explain the tug. Just darkness. The Great Attractor isn't just pulling us, it's pulling entire galaxy clusters in a cosmic game of tug-of-war. Current estimates suggest it has the mass of tens of thousands of Milky Ways crammed into a region of space roughly 300 million light-years across. Yet despite its staggering influence, it's practically invisible. Our view is blocked by the dense disk of our own galaxy, a wall of gas and dust so thick it swallows nearly all visible light from beyond. Breakthroughs have come in unexpected ways. Infrared and radio telescopes, unshackled by dust's limitations, revealed a startling truth: the Great Attractor isn't alone. It's part of something far larger, a sprawling supercluster dubbed Laniakea, Hawaiian for immeasurable heaven. Think of it as a cosmic watershed where galaxies flow like rivers toward a gravitational basin. But even this realization only deepens the puzzle. What lies at the heart of the Great Attractor? A supermassive cluster of galaxies, dark matter in concentrations we've never seen. Or something even stranger, some theories venture into speculative territory. Could it be a rare knot in the cosmic web, where filaments of dark matter intersect with unprecedented density? Or evidence of exotic physics, gravitational echoes from another universe? The wildest ideas remain untested, but that's the thrill of the hunt. Every new observation, from X-ray mappings to galaxy redshift surveys, peels back another layer of the enigma. What makes this quest so urgent isn't just the satisfaction of solving a puzzle. The Great Attractor forces us to confront how little we truly grasp about the universe's large-scale structure. It's a humbling reminder that even as we map billions of galaxies, the cosmos still holds monsters in the dark, and they're pulling us closer with every passing second. Tabby's star doesn't just flicker, it throws tantrums. Known officially as KIC 8462852, this unassuming yellow-white dwarf in the constellation Cygnus has become one of the most debated stellar mysteries since its discovery in 2015. What sets it apart? Erratic, jaw-dropping dips in brightness, some as deep as 22%, far too extreme to be explained by ordinary planets or star spots. For context, a Jupiter-sized planet would block less than 1% of its light. This star doesn't do subtle. Theories about what's causing these bizarre dimming events read like a brainstorming session between astrophysicists and sci-fi writers. The most famous and controversial suggestion: alien megastructures, specifically a Dyson swarm, a hypothetical array of colossal solar panels built by an advanced civilization to harvest their star's energy. The irregular dimming patterns, some argued, matched what you'd expect from a partially constructed swarm orbiting unpredictably. It was a tantalizing idea, one that made headlines worldwide, but the scientific community wasn't ready to call it proof. More grounded explanations point to cosmic dust as the culprit. Observations revealed the starlight dimming more at blue wavelengths than red, a telltale sign of dust grains scattering shorter wavelengths. But even this comes with puzzles. Why is the dust distribution so clumpy? Why are the dips asymmetrical, with some lasting days and others weeks? Some propose a family of shattered comets or asteroids, their debris creating a chaotic halo around the star. Others suggest an interstellar dust cloud drifting through the system, except no such cloud has been detected nearby. Then there's the star's long-term fading, adding another layer to the enigma. Over the past century, Tabby's star has inexplicably dimmed by nearly 15% overall. No known stellar behavior explains this gradual decline, leaving astronomers scrambling for analogies. Could it be the aftermath of a planet collision, with debris slowly settling into orbit, or intrinsic stellar variability so rare we've never seen its like before? Every new observation seems to deepen the mystery. In 2017, when the star's light dipped again, telescopes worldwide snapped to attention. Data revealed fine structure in the dimming, sharp, jagged drops within broader declines, as if something intricate and uneven was passing in front. Dust might explain the color dependence, but could it account for these rapid, jagged changes? The jury's still out. What makes Tabby's star so compelling isn't just the unanswered questions. It's the reminder that even in an age of precision astronomy, the universe can still throw us curveballs. Whether the answer turns out to be dust, fragments of a cosmic crash, or however unlikely, something even more extraordinary, this star has already reshaped how we approach stellar anomalies. Sometimes the most valuable discoveries aren't the answers we find, but the doors they kick open along the way. Messier 87 isn't just a galaxy, it's a cosmic predator, a celestial heavyweight with an appetite so vast it's reshaping its corner of the universe. Nestled at the heart of the Virgo cluster, this supermassive beast spans nearly 1 million light-years and weighs as much as 2.5 trillion suns. But what truly sets it apart isn't its staggering size, it's the way it feeds. Unlike most galaxies, which grow through gentle mergers, M87 is a ruthless cannibal, shredding smaller neighbors and absorbing their stars with gravitational ferocity. At the center of this galactic monster lies one of the most famous black holes in history, the very first ever photographed by humanity. 550 million times the mass of our Sun, this colossal void isn't just swallowing matter, it's launching a jet of superheated plasma 500,000 light-years into space. Imagine a blowtorch the length of 5 Milky Ways, powered by the energy of infalling gas twisted into a magnetic spiral. This jet, visible even in amateur telescopes, is a testament to the violence churning at M87's core. The galaxy's predatory nature is etched into its halo, a graveyard of stellar streams, the shredded remains of galaxies it's consumed. Recent observations reveal at least a dozen ghostly trails of stars, each a relic of a smaller system torn apart over billions of years. Some were likely dwarf galaxies, others possibly globular clusters, all now reduced to glittering debris orbiting their destroyer. This isn't just cosmic recycling, it's an ongoing feast, with M87 still hungrily pulling new victims toward its core. What makes this galaxy so scientifically invaluable is its role as a laboratory for extremes. Its black hole's jet, traveling at nearly light speed, offers clues about how such engines shape entire galaxy clusters. The plasma's structure, knotted, twisted, and occasionally flaring, hints at the chaotic magnetic fields near the event horizon. And then there's the black hole itself, a shadowy void surrounded by an asymmetric ring of fire in that iconic image from the Event Horizon telescope. That asymmetry, it's evidence of the black hole's spin, a whirlpool of space-time dragging light into a lopsided glow. But M87's dominance isn't just about destruction. By devouring its neighbors, it seeds its own future. The influx of gas from shredded galaxies fuels new star formation, while the black hole's outflows regulate growth, preventing the galaxy from bloating into chaos. This balance between consumption and creation is how giants like M87 sculpt the universe's large-scale structure, yet for all we've learned, mysteries linger. Why does its jet flicker unpredictably? How many more galactic corpses lie undetected in its halo? And what happens when M87 eventually collides with the Virgo cluster's other titans? One thing's certain, in a universe of wonders, this cannibal galaxy stands as a reminder that even the cosmos has its apex predators, and their hunger shapes everything around them. Deep in the constellation Boötes lies a cosmic anomaly so vast and empty it redefines the meaning of solitude, the Boötes void. Stretching 330 million light-years across, this staggering emptiness is one of the largest known structures in the universe, a bubble of near-nothingness where galaxies should thrive by the thousands. Instead, astronomers count fewer than 60 in that entire expanse, less than 10% of what typical space would hold. It's as if some unseen hand reached into the cosmos and scooped out a sphere of existence, leaving behind a void so profound it challenges everything we know about how the universe organizes itself. What makes the Boötes void so unsettling isn't just its size, it's the defiance of cosmic logic. The universe, at its largest scales, resembles a sponge with dense filaments of galaxies weaving around vast, empty voids. But even by those standards, this region is an outlier. Most voids span 100 million light-years or less. Boötes dwarfs them all. If the Milky Way sat at its center, humanity wouldn't have discovered other galaxies until the 1960s, their light finally reaching us across the abyss. Theories about how this void formed range from the mundane to the mind-bending. One leading idea suggests smaller voids merged over billions of years, their combined gravity pushing matter outward like a cosmic snowplow. Another posits an ancient collision between universes in the multiverse, leaving behind a scar of nothingness. But the most tantalizing and unsettling hypothesis involves dark energy, the mysterious force accelerating the universe's expansion. Could the void be a preview of our distant future, where dark energy stretches space so thin that galaxies are ripped beyond visibility? Yet the Boötes void isn't entirely empty. The handful of galaxies trapped within it huddle together like survivors in a desert, their peculiar motions hinting at unseen forces. Some race toward the void's edges as if fleeing, while others orbit invisible mass, perhaps dark matter clumps we can't detect. These oddball systems are laboratories unto themselves, their stars forged in isolation from the galactic collisions that shape most others. Astronomers have a name for regions like this, supervoids. But Boötes stands apart even in that category. Its existence forces us to confront gaps in our models of cosmic evolution. If matter was distributed evenly after the Big Bang, how did such a disproportionate emptiness arise? Surveys mapping millions of galaxies reveal no other void this large. So is it a statistical fluke or evidence of physics we've yet to grasp? Every telescope pointed at the Boötes void peels back another layer of mystery. Some detect faint whispers of hydrogen gas, the last remnants of matter too diffused to form stars. Others search for imprints in the cosmic microwave background, cold spots where the void's gravity may have sapped energy from primordial light. Each clue is a piece of a puzzle we're still assembling. What lurks in that darkness isn't just the absence of galaxies, it's a question mark hanging over our understanding of the cosmos. The Boötes void reminds us that for all our maps and models, the universe still holds pockets of profound ignorance. And sometimes the most revealing discoveries aren't found in the glittering crowds of stars, but in the silent spaces between them. If our Milky Way were a sleeping giant, the Fermi bubbles would be its ghostly breath, two colossal orbs of gamma-ray energy stretching 25,000 light-years above and below the galactic center, invisible to our eyes but blazing in high-energy light. Discovered in 2010 by NASA, a Fermi Gamma-Ray Space Telescope, these twin structures form an hourglass of violence, a remnant of some cataclysmic eruption that punched through the galaxy's disk millions of years ago. What could unleash such fury? The prime suspect sits at the heart of it all. Sagittarius, a star, our galaxy's supermassive black hole. The scale of these bubbles is hard to fathom. Each one could hold 1,000 solar systems stacked end to end, their surfaces crackling with particles moving at nearly light speed. Gamma rays, the universe's highest energy photons, leap from their edges, hinting at forces strong enough to tear atoms apart. But here's the puzzle. The Milky Way's black hole is relatively quiet today, a dormant beast compared to active galactic monsters in other galaxies. So what woke it up? One theory points to a forgotten feast. Around 3.5 million years ago, Sagittarius, a star, may have devoured a massive gas cloud or even a wayward star, triggering a short-lived but devastating quasar-like outburst. The energy released would have been unimaginable, equivalent to 100,000 supernovas launching jets of plasma and radiation perpendicular to the galactic plane. Those jets plowing through the Milky Way's halo would have sculpted the Fermi bubbles like cosmic blowtorches melting through frost. But there's a competing idea, not a single event but many. Some astrophysicists argue the bubbles are cumulative, built over eons by periodic black hole burps, smaller eruptions that piled up like layers of volcanic ash. Supporting this, the bubble's edges aren't perfectly smooth, they're lumpy, as if stitched together from multiple explosions. Then there's the wild card, dark matter. Could these bubbles be the aftermath of annihilating dark matter particles near the galactic center? It's a stretch, but not impossible. If certain theoretical particles collided and destroyed each other, they'd release gamma rays matching what we see. What makes the Fermi bubbles so captivating isn't just their origin story, it's their timing. 3.5 million years is a blink in cosmic terms, suggesting our galaxy's calm exterior might be a facade. If Sagittarius, a star, can awaken so abruptly, what's stopping it from happening again? Telescopes are now scouring the bubbles for clues, mapping their structure in ever greater detail. Every new observation peels back another layer, revealing filaments of hot gas, shock waves rippling through the halo, and hints of even older, fainter bubbles buried beneath. These aren't just relics of violence, they're a living laboratory. By studying how such energy propagates through galaxies, we're glimpsing the life cycle of cosmic ecosystems, how black holes shape their homes, how energy ricochets across light years, and perhaps how even quiet galaxies like ours hide turbulent past. The Fermi bubbles are a reminder, sometimes the most explosive secrets leave the quietest echoes. Saturn's North Pole holds a secret so geometrically perfect, it looks like nature cracked open a cosmic textbook, a gargantuan hexagon big enough to swallow 4 Earths spinning in flawless symmetry. This 6-sided storm, first spotted by the Voyager probes in the 1980s and later studied in stunning detail by Cassini, defies every expectation of how planetary weather behaves. While most storms rage in chaotic spirals, this one has maintained its razor-sharp edges for decades, possibly centuries, as if etched into the planet's atmosphere by an invisible hand. The hexagon isn't just a surface pattern, it's a towering wall of wind, a jet stream screaming at 322 kilometers per hour around Saturn's pole. Each of its 6 sides stretches nearly 13,800 kilometers, with cloud layers churning beneath in shades of gold and blue. What's truly baffling isn't just its shape, but its stubborn persistence. Earth's hurricanes dissipate in days or weeks, yet this structure has outlasted generations of human observers. So how does a storm turn into a polygon? Laboratory experiments offer a clue. When fluids rotate rapidly under certain conditions, they can form stable, geometric shapes, a phenomenon observed in spinning water tanks here on Earth. Saturn's hexagon might be a scaled-up version of this, where the planet's jet streams interact with its own rotation, creating standing waves that lock the turbulence into a six-sided pattern. Think of it like a cosmic game of tug-of-war between wind shear and planetary spin, where the forces balance just right to carve this unnatural symmetry. But mysteries linger. Why six sides? Simulations suggest the number depends on the speed and depth of the jet stream, with hexagons emerging under specific conditions. But no model perfectly replicates Saturn's freakish precision. And why only at the North Pole? The South Pole, despite similar conditions, hosts a more conventional circular storm, leaving scientists to wonder if some unseen factor, perhaps deeper atmospheric layers or magnetic fields, tips the scales toward geometry. Cassini's infrared eyes revealed another twist. The hexagon isn't flat. It's a three-dimensional beast with warm air sinking at its edges and cooler gas rising in the center, forming a towering column of weather that extends hundreds of kilometers vertically. This stacked structure might be the key to its longevity, acting like a planetary gyroscope to stabilize the shape against disruptions. The hexagon's eerie perfection challenges our understanding of fluid dynamics on a planetary scale. It's a reminder that even in the chaos of gas giants, order can emerge, not in spite of turbulence, but because of it. Every new observation peels back another layer, revealing a world where the laws of physics conspire to create something as precise as a snowflake, yet vast enough to dwarf our entire planet. And somewhere in that six-sided enigma, there's a lesson waiting. The universe doesn't just do random. Sometimes it does geometry. The dark flow is the universe's greatest unsolved mystery, a river of galaxies moving in unison towards something we can't see, like leaves caught in a cosmic current. Discovered in 2008 by analyzing the motion of hundreds of galaxy clusters, this phenomenon defies all expectations. According to the laws of physics, matter in the universe should scatter randomly after the Big Bang, with clusters drifting apart as space expands. But instead, astronomers found an eerie synchrony. Clusters spanning billions of light-years were all streaming toward the same patch of sky near the constellations Centaurus and Hydra at speeds exceeding 2 million miles per hour. This isn't just odd, it's impossible under our current understanding of cosmic evolution. What could possibly tug on so much mass? The leading theories plunge into the speculative. One jaw-dropping possibility: the dark flow is evidence of structures beyond our observable universe, other bubble universes in the multiverse, their gravity leaking into ours like shadows through a wall. If true, it would mean our cosmos isn't just vast, it's one of many, with neighboring realities exerting invisible pulls. Another idea points to primordial flaws in space-time itself, wrinkles left over from the Big Bang that warp the motion of galaxies on scales we're only beginning to map. But skepticism runs deep. Critics argue the dark flow might be an illusion, a statistical fluke or measurement error amplified by the challenges of tracking distant clusters. After all, detecting precise velocities across such distances relies on the cosmic microwave background, the afterglow of the Big Bang as a reference frame. Any misalignment in data could distort results, yet even after refined studies and repeated observations, the signal persists stubbornly real. The controversy only deepens when you consider the flow's sheer scale. This isn't a local anomaly like the Great Attractor, it's a coordinated movement spanning a quarter of the visible universe. If it's real, it implies forces at work beyond dark energy, beyond anything in our models, a gravitational anomaly rewriting the rules. Future missions, like the European Space Agency's Euclid telescope, aim to settle the debate by mapping galaxy motions with unprecedented precision. Until then, the dark flow remains a tantalizing riddle, a whisper from the edges of reality, hinting that our universe might be far stranger and far less alone than we ever imagined. Tycho's supernova should have been a death sentence, a star obliterated in one of the most violent explosions the universe can produce. Yet somehow, against all odds, a piece of it survived. This cosmic survivor, dubbed the zombie star, didn't just defy destruction, it shattered our understanding of how stars die. Back in 1572, astronomers across the globe witnessed a brilliant new light in the constellation Cassiopeia. For weeks, it outshone Venus, visible even in broad daylight, a supernova now known as Tycho's star, named after the famed astronomer Tycho Brahe, who meticulously documented it. Conventional wisdom said such explosions marked the end. Either the star would collapse into a black hole or leave behind a dense neutron star. But when scientists studied the aftermath centuries later, they found something impossible. A white dwarf, the burned-out core of a sun-like star, somehow intact amidst the debris. This wasn't just unusual, it was revolutionary. White dwarfs are stellar corpses, the cooling embers of stars too small to go supernova on their own. For one to survive, a supernova meant rewriting the rules. The leading theory: this star was a vampire part of a binary system, siphoning material from its companion until it grew unstable, detonating in what's called a Type Ia supernova. Normally, such explosions leave nothing behind, but in this case the blast might have been asymmetric, kicking the white dwarf away like a survivor blown clear of an explosion. But the zombie star didn't escape unscathed. Observations revealed it hurtling through space at breakneck speed, its outer layers scorched away, leaving only a searing hot core behind. Even stranger, its composition was bizarre, littered with elements like silicon and iron, the very materials forged in supernovas. It was as if the star had been bathed in its own destruction and lived to tell the tale. This discovery forced astrophysicists to rethink the final moments of stellar lives. Perhaps some supernovas aren't total annihilation. Maybe, under the right conditions, a star's heart can endure the inferno. The implications ripple outward, affecting how we measure cosmic distances, since Type Ia supernovas serve as standard candles for gauging the universe's expansion. If some leave survivors, our cosmic yardstick might need recalibrating. The zombie star isn't just a curiosity, it's a celestial rebel, challenging the textbook life cycle of stars. And as astronomers search for more of these undead survivors, one question lingers: if a star can cheat death, what other cosmic rules are waiting to be broken? Black holes are usually imagined as cosmic titans, gaping voids with gravity so strong they swallow stars whole. But what if I told you some are so small they could fit inside a city? Meet the unicorn, the smallest black hole ever discovered, a cosmic featherweight defying expectations. Tucked quietly near a bloated red giant star in the constellation Monoceros, this pint-sized predator packs the mass of just 3 suns into a space smaller than Manhattan. Its discovery in 2021 by a team at Ohio State University didn't just add another black hole to the catalog. It cracked open a window into one of the universe's most elusive populations. Finding the unicorn was like spotting a needle in a galactic haystack. Unlike its supermassive cousins, which announced their presence with blazing disks of heated gas, tiny black holes are notoriously camera-shy. They don't emit light, and unless they're actively feeding, their gravitational pull is subtle. So how did astronomers catch this one? The trick lay in its companion, a red giant star wobbling oddly, as if tugged by an unseen dance partner. By tracking the star's rhythmic dimming and velocity shifts, researchers calculated the invisible object's mass, too heavy to be a neutron star, yet too light to fit conventional black hole models. The unicorn had revealed itself not by what it emitted, but by how it made its neighbor move. What makes this discovery groundbreaking is the gap it fills. Black holes are thought to form in 2 main flavors: stellar mass remnants of collapsed stars, typically 5 to 10 solar masses, and supermassive behemoths lurking in galactic centers, millions to billions of solar masses. The unicorn, at just 3 solar masses, sits in the mysterious mass gap between the heaviest neutron stars and the lightest known black holes. Theory had long suggested such objects might exist, but proving it was another matter. Their formation likely requires stellar collapse under unusually precise conditions, perhaps a star pour in heavy elements, allowing it to compress further without triggering a supernova. The unicorn's red giant companion adds another layer of intrigue. Unlike the chaotic feeding frenzies of larger black holes, this pairing is oddly peaceful. The black hole isn't actively stripping material from the star. Instead, they orbit in a quiet détente. Yet the star's distorted shape, stretched slightly toward its unseen partner, betrays the relentless pull of gravity. This gentle interaction makes the system a perfect laboratory for studying how black holes influence their surroundings without overwhelming them. Why are black holes like the unicorn so rare? Part of the answer lies in their fragility. Forming one requires a star massive enough to avoid becoming a neutron star, yet not so massive that it collapses into a larger black hole. It's a cosmic tightrope walk with stellar composition, rotation, and even magnetic fields tipping the balance. And once formed, these small black holes are harder to detect unless they have a visible companion to give them away. The hunt for more unicorns is now in full swing. Each discovery could reshape our understanding of stellar evolution, revealing whether these objects are statistical oddities or a hidden population we've overlooked. For now, the unicorn stands as a reminder, even in a universe of giants, sometimes the smallest wonders hold the biggest surprises. The cosmic microwave background cold spot isn't just a curiosity. It's a cosmic bruise, a blemish on the afterglow of the Big Bang that shouldn't exist. Stretching over 1 billion light-years across the constellation Eridanus, this mysterious patch of sky is colder than its surroundings by a baffling 70 microkelvin. To put that in perspective, the cosmic microwave background, the faint glow of the universe's infancy, should be nearly uniform, with only tiny fluctuations imprinted by the seeds of future galaxies. But this is an anomaly so glaring, it's like finding a frostbite scar on a warm summer day. Scientists first spotted the cold spot in 2004, analyzing data from NASA's Wilkinson Microwave Anisotropy probe. At first, they wondered if it was a glitch, an error in the instruments, but as more sensitive telescopes like Planck confirmed its existence, the reality set in. This wasn't a mistake. It was a genuine cosmic puzzle, a place where the universe's thermal fingerprint broke its own rules. The leading theories sound like they're ripped from the pages of a multiverse thriller. One possibility, a cosmic void, a vast, empty region of space where galaxies are eerily scarce. If the cold spot is a supervoid, light passing through it would lose energy as it climbs out of the gravitational well, stretching into longer, cooler wavelengths, a phenomenon called the integrated Sachs-Wolf effect. But here's the catch: the cold spot size and temperature drop don't quite match what even the largest voids should produce. Simulations struggle to explain how such a barren region could form naturally without violating our understanding of cosmic structure. Then there's the far wilder idea. The cold spot might be evidence of a collision with another universe. In the multiverse hypothesis, our cosmos is one bubble among countless others in an eternally inflating expanse. If one of these bubbles brushed against ours in the distant past, the energy release could have left behind a thermal imprint, a cosmic kiss that chilled the background radiation. It's speculative, sure, but not impossible. The cold spot's unusual polarization patterns, detectable in Planck's data, add fuel to the fire, hinting at interactions beyond standard physics. But skeptics aren't convinced. Some argue the cold spot is a statistical fluke, a rare fluctuation in an otherwise orderly cosmic quilt. Others propose exotic physics, like primordial magnetic fields twisting the fabric of space-time. Yet every attempt to explain it away falls short of fully accounting for its stark contrast. What makes the cold spot so compelling isn't just the mystery, it's the stakes. If it's a window into the multiverse, it would be the first tangible evidence of realities beyond our own. If it's a void, it challenges our models of how structure forms. And if it's something else entirely, well, that's the thrill of the hunt. Telescopes are now scouring the cold spot for galaxies, voids, or anything that might crack the case. But until then, it remains a cosmic Rorschach test, a blank slate onto which we project our boldest theories, each one a step closer to rewriting the story of the universe. Most planets have a home, a star to orbit, a solar system to call their own, but not CFB Sir 2149-0403. This loner drifts through the galaxy like a cosmic nomad, untethered to any sun, its nights and days stretching into eternal darkness. Discovered in 2012, this rogue planet defies the usual rules of planetary science, proving that sometimes worlds get kicked out of their neighborhoods and left to wander the void alone. What makes this rogue so fascinating isn't just its isolation, it's the sheer improbability of its existence. Planets typically form in the swirling disks of gas and dust around young stars, coalescing over millions of years into orderly orbits. But CFBD Sir 2149 seems to have been ejected, hurled into the interstellar abyss by some ancient gravitational upheaval. Maybe it was a violent encounter with a larger planet, a celestial shove strong enough to send it careening into the dark. Or perhaps its star system collapsed early, leaving it orphaned before it could settle into a stable path. Either way, it now roams the galaxy at roughly 44,000 miles per hour, a speed that would take it from Earth to the Moon in under 6 hours. But here's the twist, this rogue isn't entirely alone. It's part of a moving group of young stars called the AB Doradus Association, traveling alongside them like a lost child trailing a crowd. That connection gives astronomers critical clues about its origins. By analyzing its motion and composition, they've pegged it as a relatively young planet, only 50 to 120 million years old, with a temperature of around 700 degrees Fahrenheit. That heat lingering from its formation makes it glow faintly in infrared light, the only reason we spotted it at all. Yet the real shocker came when researchers realized its atmosphere might harbor water clouds. Most rogue planets stripped of a star's warmth would freeze into icy husks, but CFBD Sir 2149 is still warm enough that its thick atmosphere could condense vapor into swirling storms, a ghostly echo of weather systems on gas giants like Jupiter. If confirmed, it would mean this drifting world isn't just a dark wasteland, it's a dynamic place, with active chemistry playing out under an endless starless sky. The discovery of rogues like this reshapes how we think about planets. They're not all neatly bound to stars, some are interstellar vagabonds, adrift in the vastness between solar systems. In fact, recent studies suggest there could be billions of them in the Milky Way alone, outnumbering stars by as much as 20 to 1. That raises tantalizing questions. Could any of these drifters host life? Might their icy mantles hide subsurface oceans, warmed by radioactive decay or tidal forces from unseen moons? It's a long shot, but in a universe this strange, ruling anything out feels premature. Every rogue planet we find forces us to rewrite the story of how planetary systems evolve. They're evidence of chaos, of gravitational billiards on a cosmic scale, where worlds can be born in one place and exiled to another. CFBD Sir 2149 is just one of many, a silent traveler in the dark, proof that sometimes the most fascinating worlds are the ones with no address at all. The Whirlpool Galaxy is a celestial masterpiece, its spiral arms swirling with such perfection they've become the textbook image of galactic beauty. But hidden beneath that pristine facade lies a violent secret, an X-shaped core, a scar etched into its heart by cosmic violence. This isn't just a quirk of perspective, it's evidence of a cataclysmic encounter, a gravitational duel between supermassive black holes that forever altered the galaxy's architecture. At first glance, the whirlpool's symmetry dazzles. Its arms, laced with young blue stars and pink nebulae, spiral outward like liquid starlight, but peer into its nucleus and the illusion shatters. There, in high-resolution images from Hubble and Chandra, the X emerges a stark intersection of dust lanes and stellar streams, cutting through the core at right angles. This structure isn't static, it's dynamic, a snapshot of chaos frozen in time. The leading theory, a black hole merger. When two galaxies collide, their central black holes eventually spiral together, unleashing gravitational waves. But before they coalesce, their competing pulls can fling stars and gas into bizarre orbits, sculpting an X-shaped debris field. Imagine two whirlpools in a bathtub merging, their conflicting currents churning the water into intersecting ripples. That's the whirlpool's core, a cosmic eddy stamped with the aftermath of destruction. Supporting this, the galaxy's companion NGC 5195 hangs ominously nearby, its gravity distorting the whirlpool's outer arms. Their dance has likely been ongoing for millions of years, a slow-motion collision that triggered bursts of star formation and funneled gas toward the central black holes. But the X suggests something more. A second, smaller galaxy may have plunged through the whirlpool's heart long ago, its black hole merging with the primary, leaving this ghostly signature behind. What makes this discovery so pivotal isn't just the violence it reveals, it's the window into how galaxies evolve. The X structure is a fossil record, proof that even the most serene-looking galaxies harbor turbulent past. And the whirlpool isn't alone. Similar X-shaped cores have been spotted in other galaxies, hinting that black hole mergers might be far messier than we once thought. Yet mysteries linger. Why does the X persist so vividly rather than fading into the background? Some simulations suggest resonance's specific orbital frequencies keep the structure sharp, like a plucked guitar string humming at just the right pitch. Others propose ongoing activity, with the black hole's jets inflating the X like a cosmic balloon. Every telescope trained on the whirlpool peels back another layer. Infrared reveals hidden dust lanes threading the X, while X-ray observations spot the superheated gas swirling around the central black hole. Together, they paint a portrait of a galaxy that survived chaos and worn it as a badge of honor. This isn't just a story of destruction, it's a lesson in cosmic resilience. The whirlpool's beauty isn't despite the X, it's because of it. A reminder that in the universe, even the most violent encounters can leave behind something breathtaking. And somewhere out there, another galaxy is forging its own X, waiting for us to decode its secrets. The Blue Ring Nebula glows like a cosmic enigma, a celestial oddity so unique that astronomers initially scratched their heads in disbelief. Discovered in 2004 but only understood decades later, this nebula defies typical classifications. It's not a planetary nebula, not a supernova remnant, but something entirely its own. At its heart lies not one star, but two, locked in a gravitational embrace, their turbulent history written in the nebula's bizarre structure, a tangle of filaments surrounded by an ethereal blue halo. What makes this object so extraordinary isn't just its appearance, it's the story it tells. The blue ring, visible only in ultraviolet light, is actually a cone of fluorescent hydrogen gas, its glow the aftermath of a stellar cataclysm. Around 5,000 years ago, the two stars at the system's center collided, merging into a single, hotter star. The violence of that impact ejected a shell of debris at breakneck speeds, which later plowed into surrounding gas, heating it until it emitted that surreal blue light. Think of it as a cosmic shockwave frozen in time, a ripple from a splash no one witnessed. But here's where it gets stranger. The nebula's central region isn't smooth. It's a chaotic web of dust and gas, twisted by the star's gravitational dance. Observations from NASA Galaxy Evolution Explorer and the Keck Observatory revealed that the system is shrouded in a thick disk of material, likely the remains of the smaller star, shredded during the merger. This disk acts like a lighthouse beam, funneling ultraviolet radiation outward and illuminating the cone-shaped halo from within. The result, a ring that's not really a ring, but an optical illusion, a trick of perspective making the cone appear circular from Earth's vantage point. The Blue Ring Nebula challenges our understanding of stellar evolution. Most merged stars fade into obscurity, their debris dissipating too quickly to leave such a vivid trace. Yet here, the aftermath persists, a neon signpost of stellar violence. Astronomers suspect the system's unique geometry. The dense debris disk and the precise angle of the outflow allowed the structure to remain visible eons after the collision. It's a time capsule offering a rare glimpse into a fleeting phase of stellar life rarely caught in action. Even the nebula's color is a puzzle. Blue is an unusual hue for cosmic gas. Most nebulae glow red from hydrogen or green from oxygen. But in this case, the intense ultraviolet radiation strips electrons from hydrogen atoms, and when those electrons recombine, they emit light at a very specific wavelength, blue. This process, called fluorescence, is the same phenomenon behind blacklight posters, but scaled up to interstellar proportions. The discovery of the Blue Ring Nebula opens a new chapter in astrophysics. It's proof that stellar mergers can leave behind more than just hotter stars. They can sculpt entire nebulae with structures we're only beginning to decode. And with new telescopes like James Webb set to study its chemistry in detail, we might soon uncover even deeper secrets. For now, this cerulean wonder stands as a reminder. Even in the cold expanse of space, collisions can create beauty, and the universe always keeps a few surprises up its sleeve. The universe sent us a visitor in 2017, an object so strange, so utterly alien to our solar system. It sparked debates that still rage today. Oumuamua, Hawaiian for scout, wasn't just another space rock. It was the first confirmed traveler from another star system, a cosmic drifter passing through our neighborhood with secrets we may never fully unravel. From the moment telescopes spotted it, Oumuamua refused to fit into neat categories. Its shape alone was bizarre, a flattened pancake or cigar, stretching up to 400 meters long but no more than 40 meters wide. Nothing in our solar system looks like this. Most asteroids and comets are lumpy or spherical, but Oumuamua's elongated form suggested a history of violent forces, perhaps tidal stretching from a close encounter with a distant star. Then there was its motion. As it hurtled away from the sun, it accelerated slightly, as if pushed by an unseen hand. At first, scientists assumed it was a comet venting gas that gave it a gentle kick. But there was no visible coma, no telltale cloud of dust and ice. Could hidden jets explain the acceleration? Maybe, but no telescope caught a glimpse. This absence fueled wilder theories. A few researchers, like Harvard's Avi Loeb, dared to voice the unthinkable. What if Oumuamua wasn't natural at all? Could it be alien technology, a light sail or probe propelled by sunlight bouncing off its surface? The idea ignited headlines, but most astronomers remained skeptical. The universe is weird enough without invoking extraterrestrial engineers. Newer studies propose a middle ground. Perhaps Oumuamua was a shard of a Pluto-like world, ripped from an exoplanet billions of years ago and packed with frozen hydrogen. As it neared the sun, the hydrogen vaporized invisibly, acting like a stealth thruster. Others suggest it's a cosmic dust bunny, a fragile aggregate of interstellar material so lightweight that sunlight alone could nudge it. Yet the mystery lingers because Oumuamua is gone, streaking out of reach before we could study it further. All we have are snapshots, a fleeting glimpse of something unprecedented. Its brief visit forced us to confront how little we know about what drifts between the stars. For every Oumuamua we spotted, how many slipped by unnoticed? The next interstellar visitor might already be on its way, carrying new clues or new riddles from the depths of the galaxy. Until then, this strange, speeding pancake remains a reminder. Sometimes the most profound discoveries are the ones that leave before we're ready to say goodbye. The Medusa Nebula slithers across the cosmic stage like a celestial gorgon, its venomous green tendrils stretching over 4 light-years, a haunting masterpiece of stellar death and rebirth. Named after the snake-haired monster of Greek myth, this sprawling cloud of gas isn't just a pretty spectacle. It's the final, violent exhale of a dying star, a sun-like giant that shed its outer layers in a fit of stellar agony. What remains at its heart is a ghostly white dwarf, the smoldering core of what was once a star, now so hot it makes the surrounding gas fluoresce with an eerie glow. What sets the Medusa apart isn't just its size, it's the chemistry dancing in its veins. The nebula's vivid emerald hue comes from a rare double dose of ionized oxygen, a signature of the star's ultraviolet radiation tearing atoms apart and coaxing them to emit light. But peer deeper, and you'll spot ruby-red filaments laced through the green, traces of hydrogen gas stirred into the mix like cosmic watercolors. This interplay of elements isn't random. It's a forensic record of the star's death throes, with different gases ejected at different stages of its collapse. The real magic lies in the turbulence. Those serpentine wisps aren't static, they're shockwaves rippling outward at over 100,000 miles per hour, the aftermath of the star's final convulsions. Imagine a pebble dropped into a pond, except the pond is made of superheated plasma, and the ripples are sculpted by magnetic fields stronger than any lab on Earth could produce. This chaos is why the Medusa looks so alive, its tendrils curling and knotting as they expand into the void. Yet for all its fury, the Medusa is a fleeting phenomenon. In about 10,000 years, the gas will disperse entirely, leaving the white dwarf to cool into oblivion. Right now, we're catching it in a cosmic sweet spot after the drama of its birth, but before the curtain falls. Telescopes like the VLT in Chile have captured its structure in stunning detail, revealing braids of gas so intricate they seem woven by some celestial hand. This nebula isn't just a relic, it's a preview. In 5 billion years, our own sun will undergo a similar transformation, shedding its skin to paint the solar system with its dying breath. The Medusa is a mirror held up to the future, a reminder that even in destruction there's beauty, and that every ending seeds a new beginning. Deep in the heart of our galaxy, something impossible is happening, a torrent of antimatter, nature's most volatile substance, gushing into space like a cosmic fountain. This isn't science fiction, it's the real, baffling phenomenon astronomers call the antimatter fountain, a geyser of positrons erupting from the Milky Way's core with enough energy to power civilizations. And here's the kicker, according to everything we know about physics, this much antimatter shouldn't exist here at all. Antimatter is the universe's ultimate doppelganger, a mirror image of ordinary matter, identical in mass but opposite in charge. When the two meet, they annihilate in a flash of pure energy, making antimatter the most efficient fuel imaginable. Just 1 gram could power New York City for days. But there's a catch. Antimatter is vanishingly rare in the natural universe, or so we thought. The Fermi Gamma Ray Space Telescope shattered that assumption when it detected gamma rays tracing the annihilation of positrons, antimatter's version of electrons billowing from the galactic center in vast structured plumes. These streams stretch 25,000 light-years into space, a testament to some ongoing process churning out antimatter on an industrial scale. So where's it all coming from? The leading theories read like a cosmic whodunit. One prime suspect is dark matter, the invisible glue holding galaxies together. If certain theoretical particles of dark matter collide, they might decay into positrons, offering a steady supply of antimatter. Another possibility involves pulsars, rapidly spinning neutron stars that accelerate particles to extreme energies, potentially creating antimatter as a byproduct. Then there's the wild card, the supermassive black hole Sagittarius, a star lurking at the Milky Way's heart. Its turbulent surroundings could be generating antimatter through processes we've yet to understand, like relativistic jets interacting with nearby gas. But none of these explanations fully account for the fountain's sheer volume or stability. If pulsars were the source, we'd expect patchy, irregular emissions, not a smooth, sustained flow. Dark matter remains hypothetical, lacking direct evidence, and while black holes are notorious for their destructive power, they're not known to be antimatter factories. This leaves scientists grappling with a tantalizing gap in our understanding, a hint that some fundamental process, perhaps entirely new physics, is at play. The implications are staggering. If we could harness even a fraction of this antimatter, it would revolutionize energy production, space travel, and more. Imagine spacecraft powered by milligrams of fuel, or cities running on particles that weigh less than a snowflake. But the fountain isn't just a potential resource, it's a cosmic mystery box, forcing us to reconsider how matter and antimatter behave under extreme conditions. Every new observation peels back another layer, revealing a universe far stranger and far more generous with its secrets than we ever dared to dream. The universe loves blurring the lines between what we think we know, and the Elst-Pizarro Comet asteroid hybrid is the perfect example of cosmic rule breaking. Discovered in 1996 orbiting between Mars and Jupiter, this object looks like a typical asteroid at first glance until it suddenly sprouts a tail like a comet, spewing gas and dust into space. Astronomers were stunned. Asteroids aren't supposed to do that. They're rocky relics frozen in time since the solar system's birth. Comets, on the other hand, are icy wanderers from the outer solar system, glowing with vaporized ices as they near the sun. So what's this oddball doing with an identity crisis? One camp argues Elst-Pizarro is a failed comet, a celestial refugee that started life in the icy outer solar system but got flung inward long ago, its volatile ices mostly baked away by eons of sunlight. What little remains might lurk deep beneath its surface, erupting in sporadic outbursts when fractures expose it to space. This would explain its occasional tail, a brief gasp of activity before it settles back into rocky anonymity. Supporting this, its orbit matches the main asteroid belt, where temperatures are too high for significant ice unless it's a recent arrival. But another theory suggests something far more revolutionary. Elst-Pizarro might be the first known member of an entirely new class of objects. Main belt comets, as they're tentatively called, could be native to the asteroid belt, harboring subsurface ice despite the region's warmth. How? Perhaps they formed with a protective layer of dust, a thermal blanket shielding ancient ice from solar radiation. Or maybe they're proof that the asteroid belt once extended much farther out, trapping volatile materials before migrating inward. Either way, their existence would rewrite textbooks, proving ice isn't just the domain of distant comets. The debate isn't just academic, it's a window into the solar system's hidden plumbing. If objects like Elst-Pizarro are common, they could be secret reservoirs of water, delivering it to the inner planets via impacts over billions of years. That would make them key players in Earth's own origin story, possibly even contributors to the oceans we swim in today. Recent surveys have spotted more of these hybrids, hinting that Elst-Pizarro isn't alone. What truly captivates scientists is the unpredictability. Unlike regular comets whose activity peaks near the sun, these objects flare up erratically. One hypothesis suggests impact activation, tiny collisions cracking their surfaces and releasing trapped gases. Others point to rotational instability, where spinning too fast causes structural failure, exposing fresh ice. Every outburst is a clue, a fleeting chance to study processes we've never seen elsewhere. Elst-Pizarro doesn't just defy categories, it challenges our assumptions about how rigid those categories should be. In a universe full of exceptions, maybe the real lesson is that nature doesn't care about our labels. Whether it's a refugee comet or the pioneer of a new breed, this cosmic chameleon reminds us that the solar system still holds surprises, and the most interesting discoveries often lie in the gray areas between what we think we know. Then there's KIC 8462852, not just another twinkle in the Kepler telescope's data, but a star so baffling it's earned its own ominous nickname, the Dyson Sphere Candidate. Like Tabby's star, this distant sun flickers unpredictably, dimming by staggering 20% at times, as if something colossal is passing in front of it. But while Tabby's antics could be blamed on dust or cosmic debris, this candidate takes the strangeness further. Its light curves don't match any natural phenomenon we've seen, no cometary swarms, no planetary collisions. Instead, the dips are sharp, asymmetrical, and alarmingly precise, as if engineered. The Dyson Sphere hypothesis, once relegated to sci-fi, suddenly doesn't seem so far-fetched. Proposed by physicist Freeman Dyson in the 1960s, the idea was simple. An advanced civilization might harness its star's energy by building a vast swarm of solar collectors, a megastructure enveloping the sun. From afar, such a construct would block starlight in unnatural patterns, exactly what some argue we're seeing here. The candidate's erratic dimming resembles theoretical models of partial Dyson swarms, with uneven structures rotating in and out of view. Skeptics, of course, have counter-arguments. Could it be an undetected debris disk warped by gravitational tides into jagged, light-blocking shapes? Maybe. But debris typically glows in infrared heat from countless tiny particles, and this star shows no such excess. Others propose a family of hyper-dense planets with bizarre orbits, though no known physics explains their formation. The truth, we're stuck in a cosmic detective story with too few clues. What sets this candidate apart from Tabby's star is the unnerving specificity of its anomalies. While Tabby's dimming could be written off as dust's wavelength-dependent scattering, this star's light drops don't play by those rules. They're agnostic to color, blocking all wavelengths equally, a hallmark of solid objects, not diffuse clouds. It's as if something opaque and massive, something utterly unnatural, is methodically eclipsing the star. Yet before we hail this as proof of alien engineers, remember, the universe loves throwing curveballs. Protoplanetary disks can warp into weird configurations. Stellar magnetic fields might twist plasma into temporary occlusions. Even the most tantalizing data requires extraordinary evidence. But that's the thrill of the hunt. Whether this candidate is a megastructure, a cosmic oddity, or something beyond our current science, it forces us to confront a humbling truth. The universe isn't just stranger than we imagine, it's stranger than we can imagine. And somewhere in that mystery lies the next revolution in how we see the cosmos. The universe has a way of turning cosmic monsters into cosmic fugitives, and nothing proves that better than the runaway supermassive black hole blasting through intergalactic space like a bullet through silk. Astronomers first caught wind of this anomaly in 2022, spotting an inexplicable streak of young, blue stars stretching an astonishing 200,000 light-years across the void. But here's what froze them in their tracks. At the tip of this stellar contrail, racing ahead at 4 million miles per hour, was the unmistakable glow of a black hole weighing as much as 20 million suns. This wasn't just drifting, it was fleeing. So what could possibly kick a supermassive black hole, an object so gravitationally dominant it anchors entire galaxies out of its home? The leading theory reads like a gravitational thriller. Most galaxies, including our Milky Way, host colossal black holes at their cores, locked in place by the combined pull of billions of stars. But when galaxies collide, their central black holes eventually spiral toward each other, merging in a cataclysmic dance. During this violent tango, if a third galaxy crashes the party, the chaotic three-body interaction can fling one of the black holes into the abyss like a slingshot. Simulations show these ejections are rare, requiring an almost impossible alignment of mass and momentum, but when they happen, the recoil is spectacular. The runaway star trail adds another layer of awe. As the black hole plows through intergalactic gas, it compresses the material in its wake, triggering bursts of star formation. Picture a cosmic plow tilling the darkness, leaving a furrow of newborn suns in its path. These aren't just any stars, they're young, hot, and unusually dense, clustered in a straight line that defies the usual swirling patterns of galaxies. It's evidence of the black hole's messy escape, a breadcrumb trail of chaos pointing back to whatever catastrophe birthed it. Yet mysteries linger. Hubble's deep field images reveal no obvious wreckage of a galactic collision at the trail's origin, suggesting the violence occurred so long ago that the debris has dispersed. Some astronomers speculate the black hole might have been ejected not by a trio of galaxies, but by an asymmetric explosion of gravitational waves during its merger, a kick so powerful it overcame the gravitational pull of its entire host galaxy. Others wonder if dark matter played a role, its invisible scaffolding guiding the black hole's trajectory like an unseen hand. The implications are staggering. If black holes can be evicted from their galaxies, how many others are drifting unseen in the darkness? Could these rogue titans seed star formation in the desolate voids between galaxies? And what happens when one approaches another galaxy? Does it carve a new home or tear through like a bull in a cosmic china shop? Telescopes are now racing to track more of these renegades, each one a testament to the universe's untamed violence. After all, in a cosmos where even the mightiest monsters can become outcasts, nothing is truly anchored and nothing is safe. The giant arc of quasars stretches across the cosmos like a bridge between realities, a formation so vast it challenges the very foundations of modern cosmology. Discovered in 2021 by astronomers combing through data from the Sloan Digital Sky Survey, this structure defies logic, a near-perfect curve of quasars, those blazing cores of ancient galaxies aligned across 9 billion light-years. To put that in perspective, if you could travel at the speed of light, crossing this arc would take twice the age of Earth. And yet, here it is, a cosmic question mark etched into the fabric of the universe. What makes the giant arc so disruptive isn't just its size. It's the way it seems to spit in the face of the cosmological principle, the bedrock assumption that on the largest scales, the universe should look roughly the same everywhere. Matter ought to be distributed evenly, like sprinkles in a well-mixed cake. But this is a crack in that logic, a filament of quasars so colossal it shouldn't exist under our current models. Quasars themselves are no mystery, they're supermassive black holes at the hearts of young galaxies, gorging on gas so ferociously they outshine entire galaxies. But finding them strung along a curve, like pearls on an invisible necklace, suggests something far stranger, a hidden scaffold of dark matter or primordial energy weaving through the cosmos, tugging these objects into alignment. Some researchers argue the arc might trace a shockwave from the Big Bang itself, a fossilized ripple in space-time frozen in the act of shaping the universe. Then there's the unsettling symmetry. The arc isn't just big, it's geometric, following a consistent curvature that feels almost intentional. Natural structures this size should fray at the edges, blurred by billions of years of cosmic expansion. Yet the giant arc holds its shape as if the universe pressed a cookie cutter into the heavens. Critics push back, of course. Could this be a statistical fluke? A trick of perspective where unrelated quasars appear aligned from our vantage point? It's possible, but the odds are vanishingly slim, like rolling a million dice and having them all land on 6. Others suggest we're seeing the ghostly imprint of cosmic strings, hypothetical defects in space-time left over from the universe's birth. These ultra-dense threads, thinner than an atom but stretching across galaxies, could theoretically warp the distribution of matter around them. Every new observation deepens the mystery. The arc's quasars aren't just aligned spatially, they share similar redshifts, meaning they're roughly the same distance from Earth. This isn't a random assortment, it's a structure, a backbone of the cosmos we never knew existed. And if one such arc exists, how many others lurk undetected? The giant arc forces us to confront an uncomfortable truth. Our maps of the universe might be embarrassingly incomplete. Either we're missing a fundamental piece of physics, or the cosmos is far more structured and far stranger than we ever imagined. Either way, this isn't just an oddity. It's a revolution waiting to happen. From pulsars that devour their stellar companions to rogue black holes fleeing their galaxies, each of these 25 cosmic oddities has rewritten the rules of astrophysics in its own bizarre way. The Black Widow Pulsar taught us that stars can be predators, while the zombie star proved even supernovas can leave survivors. The Great Attractor showed us invisible forces sculpting the universe, and the dark flow hinted at realities beyond our own. We've wandered through voids so vast they defy logic, marveled at hexagonal storms on Saturn, and questioned whether megastructures might lurk around distant suns. Every discovery peeled back another layer of cosmic mystery, revealing a universe far stranger than our textbooks ever imagined. But here's the beautiful truth: these aren't just anomalies, they're invitations. Every time we point a telescope at the sky, we're not just collecting data, we're stepping into the unknown, where the next observation could upend everything we thought we knew. That's the thrill of astronomy. The universe doesn't just surprise us, it dares us to keep looking, to stay curious, to embrace the discomfort of not having all the answers. So which of these cosmic riddles captivates you the most? Is it the diamond planet glittering in the darkness, the eerie hexagon spinning atop Saturn? Or something even wilder, like the possibility that antimatter fountains or colliding universes might be hiding in plain sight? Drop your favorite in the comments, or shout out a space mystery we didn't cover. Because the wildest part of this journey isn't the strange objects we've found, it's the ones still waiting to be discovered. And who knows, the next great cosmic revelation might start with a conversation right here. After all, the universe isn't finished surprising us yet, not even close.